Hello everyone, welcome to this video all about geometric operations, which is a type of measurement and data question. This video is going to focus on the topic called tessellation. So let's begin by reading a brief description of what we can expect in tessellation questions. Tessellation is the arrangement of shapes that are closely fitted together, usually polygons, without leaving gaps or overlapping. Tessellation questions are focused on patterns formed usually by 2D shapes. Tessellation questions can use a variety of shapes, and so it is important that we have thorough knowledge of 2D shapes. Ratios can also be useful in working out tessellation questions. Okay, so even if the word tessellation sounds a bit fancy, at the end of the day, it's just a phenomenon of arranging shapes and making sure that they don't actually overlap or have any gaps when you draw them. So it's a design that you commonly see with tiles or mosaic art, and all of those use the mathematical concept of tessellation. So for example, if we have triangles, they're actually really good at tessellation. And if we have multiple triangles and you join them together at the edges like this, then this is an example of a tessellating pattern. And that's because all of these triangles are joined together at the edges and there's no gaps in between the edges at all, which is why this is tessellating. Tessellating design. So for example, things like circles can never be tessellating shapes, and we can quickly see why if we draw one. If we have one of these and we've got multiple, let me see if I can do this, and we have multiple of these circles, they're never going to tessellate, but just simply because of the nature of circles means that the lines will never fully align. There's going to be a gap between the circles, and if that happens, then these shapes can't be called to be tessellating. So most of the time when we have tessellating questions, we'll be seeing shapes with straight edges, though it is possible for some curved shapes to be tessellating. So for example, if we had something like this, then we definitely could make it tessellate by having multiple of these. And we can see this, even if it did have these curves, the way the shape looks allowed it to tessellate perfectly without any gaps, unlike the circle. So tessellation is a fairly straightforward topic, as these generally just involve the drawing of patterns with different shapes and making sure that there are no gaps when you make the pattern and there are no overlaps. So for example, if we have let's draw a random shape. If we try to, that's not a random shape. If we draw a random shape like this and we try to make it tessellate, if you have multiple of these overlapped each other, then all of a sudden, the second you have overlapping, then it's no longer considered to be tessellating either. It has to perfectly align at the edges and leave no gaps. So fairly straightforward, but there's one interesting thing with tessellation that we might mention now. When you're doing tessellation with regular polygons, and those, if we want to just briefly mention the difference between regular polygons and irregular polygons. Regular ones are the stereotypical shapes we usually see. So for example, a regular quadrilateral would be a rectangle. A irregular quadrilateral would be a quadrilateral where none of the internal angles are actually the same. So when we're talking about polygons that are regular, so all of the internal angles are the same, we can quickly see that if we try to tessellate these kinds of polygons, then if we take a look at the corner of these tessellating shapes, so in this case scenario would be this corner, we can see that if the internal angles of the shapes add up to 360 or be a factor of 360, a multiple of 360, then it's obviously going to tessellate. So all quadrilaterals are going to tessellate because their internal angles are always 360 degrees. But if, for example, we're dealing with a regular pentagon, a pentagon has, oops, let's see if I can fix that. Yes. So a pentagon has 540 degrees as its internal angle sum. So if you add all these angles together, you get 540 degrees. And 540 is not a multiple of 360, since the next one is 720. So if you try to tessellate a pentagon, you'll see that it doesn't work. So if I've got multiple of these, and try and tessellate them, we can see quickly that there's just no way that they can be arranged to tessellate without leaving gaps like these. So that's just something interesting that we can keep at the back of our minds when we're dealing with tessellation questions. Now, let's see if we can tackle this example question. Anna is making a rectangular rug using two different squares, a larger square and a smaller square. The diagram below shows an incomplete version of the rug, but with its final length and width. The question is, how many small squares must Anna use for the whole rug? Okay, so even though the question has given us the dimensions of the little squares, it looks like they don't have any relevance to figuring out the answer of the question. So it's always important that we filter out only the important and relevant pieces of information to a question so that we don't waste any time or that we don't get led astray by the useless piece of information like the dimensions of the tile in this question. So we can take a look at the rug design and quickly see that it is in fact a tessellating design. All of the squares line up perfectly, and since the squares are a type of regular polygon, we talked about how quadrilaterals will always tessellate. So that's just an interesting thing we're seeing here. So we can quickly see the tile design is being repeated in this kind of structure where they've got, Anna has one of the larger pieces and she's got 1, 2, 3, 4, 5 of the smaller pieces. So in each one of these larger shapes, it looks like this, we've got one of the X's, and for the Y's, we've got 1, 2, 3, 4, 5 of them. So that kind of helps us figure out how many there are fairly quickly without having to count each one. We can see that there's 1, 2, 3, 4 of these full square designs, and this one doesn't actually have the extra tiles at the end, so let's discount that for now. But we can see that there is 4 full squares per row, and there's 1, 2, 3, 4 in this row, 1, 2, 3, 4 in this row. And again, like this column here, there's actually this lower row which doesn't utilize the full design. So for now, we can quickly calculate that since there were 1, 2, 3, 4 and 1, 2, 3, there's going to be 12 of these large squares in total. So since we're only concerned about the smaller squares, 5 times 12 is equal to 60. So 60 small squares have been used in this part of the design. But obviously that's not the final answer because we do have these extra sections at the end that we haven't accounted for yet. And I think honestly just counting those would be faster. So let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 14 of these smaller squares being involved. So it looks like we have a grand total of 74 squares. So looking down at the answer options, we can circle option B as the final answer. Okay, so we saw that tessellation questions are fairly straightforward. We just need to know that the patterns are formed by joining shapes that don't overlap or leave any gaps, and we just had to count and see which numbers were relevant in the question. So hopefully that is all the techniques that we may utilize in future tessellation questions. Thanks so much for listening to this video.